I'm going to talk about the final exam from 2021. And one thing to point out is that this was another year of COVID, and so a slightly different format. The content is pretty much the same, and the expected concepts are the same year by year. And you can see that by looking at the final exam of 2020 or any of the previous years. And I'll try and highlight some of the main ideas. So really the goal here is what did we cover on the 2021 final assessment, and final assessment was the jargon used for that particular year. It's a final exam, and the content and expectations pretty much align with what we've done in the past. And so the first question looked at a toy vehicle or toy vehicles. And what's happening is that you have two vehicles, A and B, that are going to collide, and they collide at location C. After the collision, both vehicles have their brakes locked and are locked and slide to a new position. And so as they slide to the new position, they end up moving in two different distances. The mass of each of the vehicles is the same, 1.85 kilograms, so it's toy cars. Velocity of A just before impact is given as 9 kilometers an hour to the right. And mu sub K, the force, the friction coefficient, kinetic friction, is 0.3 for both vehicles. You're asked to find the speed of the vehicle A, the speed of vehicle B immediately after collision, so both after collision, and the speed of vehicle B just before collision. So you have these two, which are related to one concept, and these, which is related to another. So after impact, you have the vehicle that starts with the initial velocity, 1/2 ma va prime squared, that's 9 meters per second, and you know that it slides to a stop. So A has slid from point C to point A. Or to 4 meters, pardon me. And TA2 then is equal to 0. In order for it to actually do that, it's going to have a force of friction. And force of friction times 4 meters is going to be the work done. And you should note, and I probably should have done this, that this is going to be negative because the work done is going to be in the opposite direction of displacement. So you have mu k mag, and you end up with the initial kinetic energy plus the work done equals the final kinetic energy. That's 0, and that is TA1. And you end up with VA prime, which is 4.85 meters per second. So work energy here, because the vehicle is sliding, there's no impact, nothing has occurred outside. After impact, the two cars come together, or after impact for car B, it slides only 1 meter. And because it only slides 1 meter, it has an initial kinetic energy, just like car A. It has a final kinetic energy, which is 0, but it only slides 1 meter, and so there's a negative there. And so if I add up the terms, I get 2.426 meters per second. You don't have to be that exact. You want to probably have 2 digits on your terms. So at C, the question was, just before impact, what was the velocity of car B? You know, this is 9 meters per second, and we've just solved for these two velocities, 4.85 meters per second for A and 2.426 meters per second for B. So that's the only unknown. All of these are the same in terms of masses, so you can get rid of those. And so you end up with a final velocity of B, which is 9.78 meters per second. And what were we looking for? We were looking for work energy. Both particles move and work is done by friction. And on the second term, we have conservation of momentum. And really, this is a first half of the course problem looking at particle momentum and work energy. Here we have a square panel. this is the second question, which has a radius of 9 kilograms and a length of, a mass of 9 kilograms and a length of 2.5 meters on each side. So 2.5 meters, 2.5 meters, and 9 kilograms. Its radius of gyration about its center is 0.8 meters. So we could just do that. Radius of gyration, RG or KG. The panel is initially hanging by 2 vertical wires attached to the panel at points A and B. You cut point A, and that's time 0. What is the angular acceleration of the panel and the tension in the wire at point B immediately after the breakdown or break occurs? Use the coordinate system shown in the diagram, and here's your coordinate system. X is positive to the right, Y is positive to up, and counterclockwise standard direction. Gravity is given to you in this, and here's your ceiling. So everything's pretty much a standard sort of setup. So you need to do some moments about G. You need to do it about the center of mass. You can't use another point and use parallel axis theorem because the thing is accelerating. And so you don't have a stationary point. So sum of moments about G equals mkg squared alpha. And you can put in the terms. You only have tension, which is acting upwards, and you have weight, which is acting downwards. So tension doesn't cause a moment, or excuse me, tension causes the moment, weight does not. Substituting in terms, you know it's 1.25 t from the point B to the center of mass. That whole distance is 2.5. This distance, of course, is going to be 1.25 meters. And you get a tension of 4.68 alpha. Term here, you are given K sub G, you're given the mass. Alpha is the only unknown. So you have a relationship between tension and angular acceleration. Sum of forces in Y, you have tension up, you have weight down, and you have the acceleration in Y, which you don't know. So you have T minus the weight equals 9 acceleration Y. But you do know the acceleration of Y is going to be L over 2 times alpha, and so you can relate one to the other. It's minus 1.25 alpha. All right, so we have these terms. We have the acceleration of the center of mass. Everything's good. Combine all the terms and get all of this together, and you end up with substituting in all of your terms here. You end up with T equals 25.65, 25.7 newtons, and alpha, which is 5.6 rads per second squared. This was the rigid body kinetics problem, and so it was useful for that. Here you have a 75 kilogram wheel, which has a radius of gyration with respect to G of 0.9 meters. Pulley A is massless and runs on frictionless bearings. The inner radius, you can see right there, is 0.8 meters, and the outer radius is 1.2 meters. A rope is wound around the inner hub of the wheel, and the wheel is rolling initially at 10 rads per second counterclockwise. The wheel is rolling without slip on the ground. So that's kind of useful because then you can do our standard no-slip relationships for alpha in this case. Please use the coordinate system shown in the diagram. So you have x positive to the right and y positive downward. And here you're going to do a clockwise positive rotation. Draw the free body diagram. So this was kind of tricky in that sense. You really do have to read carefully the problems. Draw the free body diagrams. How much time will it take for it to roll at 6 rads per second clockwise? What are the initial? Wheel is rolling at 10 rads per second counterclockwise, and final wheel is rolling at 6 rads per second clockwise. Speeds at the point B as shown on the figure and the top of the inner point, hub point at all times, so right here, this point. One of the issues that comes up is where exactly is the zero velocity point? Typically, when you deal with problems like this, we say it's rolling on the surface, and therefore this point is 0, and everything's okay. In the lectures, hopefully at this point, you've seen a couple examples where we have a wheel moving along a pulley or a rope. And in those cases, the zero velocity point ends up being this point right here with the large green circle. So the initial velocity is given as 8 meters per second. And so it has to be referenced with respect to that zero velocity. And the final velocity of g is given as 6 rads per second, and that ends up being 4.8 meters per second. This is based on using the recommended axes. Velocity of b in all cases is 0, and if you calculate velocity of b g initial and vb g final, you get 8 and minus 4.8 in order to cancel out g's velocity at that point. So using the principle of impulse momentum and the solutions we've just obtained, we know that we can use mvgx1 plus the sum of all the impulses is the final linear impulse of the system of the wheel. We can do the same thing for the mass on that string, this mass over here, and tension's up, weight is down, tension over here, weight acting downwards, normal force, and friction force. So putting all of this together and adding them in, we then can create a set of equations to solve based on the information we have. T minus F. We're not doing anything in the y direction for the wheel because it doesn't matter. We do it for the mass because it is moving. And then for the angular momentum, we add in the other terms, and the solutions we were given minus 10 and 6 as the two beginning and end points. If you solve through for everything, you'll end up with a force of 62.66 newtons, a tension of 448, 450, 448.23 newtons, and a time of 2.5 seconds, 2.49. Finally, or not finally, there's two more questions. Wheel is rolling without slip with a constant angular velocity of 5 rads per second. Link BC is connected to slider B. So this link right here is connected to the slider B. Point C is right at the top edge of the wheel. Find the velocity and acceleration of slider B for the position shown where theta is equal to 30 degrees and r equals 100 millimeters. Use the coordinate system shown. So one of the things that's important in this course is kinematics, of course, and we kind of look at various aspects of the geometry here, and I just want to sort of point out a couple of things. First of all, I don't know what the angle of this link BC is, and so it would be helpful to know that. But I did get that it's 300 millimeters or 0.3 meters. And I also know that I can define a term, for example, right here, gamma, and gamma is going to tell me what that angle is. So the total height, the 300 millimeters, is just going to be the vertical distance of BC plus 2r, which is the distance along the height of the cylinder, so its diameter. Substituting in terms and extracting, well, there you go, a little bit out of sync, I get gamma is equal to 60 degrees. From this, I can say velocity of c, which I already know is the omega of the wheel, which is given, times 2r, which is the diameter. So from the point of contact down here, which I could call O, it's going to be 1 meter per second. So I have 5 rads per second in the clockwise direction, so it's a negative value cross with 2r, which is positive. To calculate the velocity of B, I would just need to know what velocity of C is plus velocity of B relative to C. Now, the one thing I do know is that the velocity of B is constrained to move along this line, and I'm pretty safe in assuming that it's going to move vertically upwards and to the right. So using the coordinate system shown, and the reason why we give you these coordinate systems often is to help you, I can say velocity of B is equal to VB cos 30, which is theta, VB sine theta, which is 30 again, velocity of C, which I've just calculated over here, plus omega BC crossed with minus LBC sine lambda, so this distance here, plus LBC cos gamma, and gamma again is this angle here, or lambda, sorry, lambda, I keep wanting to call it gamma. Substituting in terms and separating out the I and j components, I get velocity of b cos 30 plus LBC omega BC cos lambda equals VC, VB sine 30 plus LBC omega BC sine of lambda equals 0. So I have two equations, two unknowns. Those two unknowns, of course, are velocity of b and omega BC. Substituting everything in, calculating and solving the simultaneous equations, I get 1.73 meters per second for velocity of b and omega BC, which is 5 rads per second clockwise. It's an interesting, this part of the problem is just a review of the geometry, and if you solve it in this vector form, it's pretty straightforward. But the tricky bit here is really recognizing these distances. So having a negative here and a positive here, because everything is relative to point C. Okay, so moving on. So the next part of the problem is solving for the acceleration of B. Again, kinematics problem, standard things that we expect from you on an exam. So we have acceleration of B, which is equal to acceleration of C plus acceleration of B with respect to C tangential and normal. So everything is now with reference to C, and we don't really know anything about point C. But we do know point C with respect to point O, and point O is down here. So if you look at acceleration of point O, and you know that alpha in this particular case is 0 because it's going along, you also know that you have an acceleration in the normal direction. And we've talked about this in a number of different cases, but omega squared RC with respect to O. So in the end, you end up with R omega squared J minus twice R omega squared J, and you end up with that equal to minus 2.5 J meters per second squared. Acceleration B with respect to C tangential, the alpha BC crossed with the distances, and acceleration B with respect to C normal, which is just going to be this right here. Moving on, you have then the acceleration of B in terms of its cos and sine components, which you know from the geometry, and you have that theta right there. I didn't talk about the gamma, but we talked about gamma in the last slide. So there's ACJ minus LBC alpha BC cos gamma LBC LBC alpha BC sine gamma J plus omega B squared LBC sine gamma I, and I don't know why I did these hats, but okay, omega B C squared LBC cos gamma J. So at the end, you end up with your X and Y components right there, and I jumped the gun again a little bit, but this is your I right here, and this is your J with the correct sort of form. And you end up with acceleration B, which is 12.5 meters per second squared, and alpha BC, which is 64.95 rads per second squared. It's a rigid body kinematics problem. It is part of the dynamic concept inventory, and something I should be stressing more as I continue with doing these types of videos and solutions. But the main point here is that this is a fundamental concept in the course. The approach taken is a fundamental approach. Please make sure that you know what it is. And finally, we have this, which is a system which consists of a wheel that's pinned at G. Outer radius and inner radius are given as 0.12 meters and 0.06 meters, respectively. Spring constant 1 is 130 newtons per meter. Spring constant 2 is 390 newtons per meter. You have a dash pot here, and that has a constant of 55 newtons second per meter. And you're asked to find what is theta of the system at t equals 0.02 seconds. The system is released from rest with an initial displacement of theta, here's theta, which is equal to 0.03 radians. So if I put all the terms in, I have force of spring 1, I have force of spring 2, I have force of the dash pot, I have the pin forces x, y, and I have weight, which is acting downward. So I could do sum of moments about g, which gets rid of all of these terms. And I have minus Fc plus Fs1, which is acting at a distance r0. And I have Fs2 Ri, which is acting at the inner radius. Now, what was really important in this particular problem was recognizing that you needed to solve it with moments. And then you can say Ig alpha, here it's alpha d, the wheel. You know all of the terms, K1 R0 theta, K2 R I theta, that's spring displacements. And here you have to have a velocity. And so that's the R0 theta double dot. Alpha d is just going to be theta double dot, just substituting in so we have consistent notation. So once you do all of the terms and you break it up into theta double dot, and theta, you then have an equivalent mass for the system. You have an equivalent dash pot constant, and you have an equivalent spring constant. So that's what we use to make to figure out the solution to this. And so often the challenge is to recognize that spring constant is not necessarily the spring constant of the term, and in particular in this problem, you had two moments to deal with, and that's R0 squared and Ri squared. Substitute in definition, critical damping coefficients twice square root K equivalent and mass equivalent. Put in all the terms, and you solve through. So you end up with a damping coefficient of 5.65, which is right up here. The natural frequency for the system is K over M, and so K over M is K R0 squared plus K2 Ri squared over I sub g, and that ends up being 46.63 rads per second. We can substitute all of this back in, so I'm going to regret this, but you put the omega or the squiggly zeta in there. You have all of the terms that you need. You already have omega n top, and you can put all of them in. Now, the way I've written it here is not the way you would write it on a final exam, and it looks overly complex. In a final exam, what you would do is take these terms and make them into constants, and then it becomes not so bad. But this term right here, or this expression right here, would just be a theta equals e to the minus at, or c1t, ae c2t, plus be to the minus c3t. And then you substitute all the terms in. You can try it on your own. You can probably do it all together, and it certainly would be easier to write. And at this point, if I weren't doing a final exam solution, that's how I would present it. Substitute in all the expressions you know at theta equals 0, it's displaced by 0.05 rads. That tells you a plus b. Then you know theta dot at 0 time, and so you then put in all the terms there. You then get a and b, 0.0302 and negative 0.0002. So that's your equation, and that's kind of important. That's where you're going with all of this. E to the minus 264t, 0.302 e to the 259.283t plus minus 0.02 e to the minus 259.83t. Now, if I had been a little bit smarter, I would just multiply all of this across, and I'd end up with a big number of about 500 and a small number of about 4 here. And I didn't. I solved it, and actually I did. There you go. There's the solution if I'd just been a little bit more clever. But theta equals 0.02 seconds. I have 1.59 degrees, and that's equivalent to 0.028 rads. And of course, as you're doing these problems, you do want to solve them in radians, not in degrees, but we're a little bit more forgiving on final exams, a lot more forgiving on final exams for this sort of thing. So degrees or radians would have been an equivalent and not an issue. So what were we testing on? Free damp vibration, no surprise, that's the last 2 to 3 weeks of the course. One of the things that comes across is that you have to be very careful in how you read the questions. These questions were on a screen. Typically, year by year, we'd put them on paper and you sort of read them, mark them up, make sure you know exactly what you're looking at. Another thing is often students try and solve these problems without really drawing a picture. Draw a picture, then figure it out. And if you draw the picture, it becomes a lot easier. And I kind of encourage you to do that when you're dealing with your final exams. Hopefully this was helpful. Thank you very much, and we'll talk later.